What's up guys, welcome back to Dynamic Programming for Beginners. This is part 16 and real quick I wanted to record this video about the change making problem, which is also a problem about coins. It's a classical problem, sort of like a foundational as well. It's a combinatorial problem I'm sorry, this is an optimizational problem because we have to optimize a function here, and the idea behind this problem is that we have to find the minimum number of coins to make a change of size n. So in the previous few lectures we were talking about coin change problem, in which we had to find the total number of ways to make a change, and today we want to find the minimal number of coins to make a change. So let's take a look at a quick example. So let's say n equals to 4. So in the coin change problem we would try to find the ways to make 4, right? And that would be 1 3 1 1 1 1 3 1 and that's it, right? In the change making problem we have to find the minimum number of coins to make this amount. So the minimum number of coins is 2, so f equals to 2. It's basically 1 cent and 3 cents. We don't have any other denominations that would let us make this change. So this is the idea behind this problem. What's the intuition? How are we going to solve this problem? So the first idea that may come to your mind is to always use the highest coin, and that will kind of like give you the minimum number of coins. And that's kind of like logical, right? So if you need to make a change of a certain amount, you basically can take the coin with the highest denomination, kind of like return it, then take another coin of the highest denomination, and at some point you will return you will use the minimum number of coins to make a change. But unfortunately this logic is not always correct. So let me show you an example. So let's say the coins, the denominations that we have are, let's say 1, 4, and say 5, right? And n equals to 8. So according to the greedy approach, right, when we take the highest denomination, the very first step would be to use 5 cents, right? So we return 5 cents, and in this case, n equals to 3. After that, we may want to try to return 4 cents, but we can't return 4 cents because n is 3. So what are we going to do? We'll return 1 cent. Now n equals to 2. What do we have to? No, we don't. So the third step would be to return 1 cent again. Now n equals to 1. And the last step, we simply return 1 cent. N equals to 0. So we made the entire change. So the answer is 5 1 1 1, and the minimum is 4. Right? So in this case, f equals to 4. Well, whereas the optimal solution to this specific setup is returning 4 cents twice, right? 4 and 4. This would be the optimal answer. F would equal to 2. So this is the problem with the greedy approach. Basically, not all the denominations would result in an optimal solution with the greedy algorithm. So let's take a look at dynamic programming solution. The knowledge that you have so far, this is lecture 16, should be enough to solve this problem, but I just wanted to review it together. So the first step is to define the objective function. And in this problem, defining the objective function is very simple. F of I is the minimum number of coins to make a change of size I. F of I is the minimum number of coins to make a change of size I. Let's take a look at base cases. So f of 0. What's the minimum number of coins to make a change of size 0? Basically, we can use 0 coins of each denomination, right? And this would be 0. This is the minimum number of coins to to make a change of size 0. f of 1. What's the minimum here? So the minimum is 1, right? It's one coin. Remember, it's not a waste, it's a coin. So we would use one coin of 1 cent. f of 2 would equal to 2. We would use one coin, 1 cent, and 3. What about, let's say, f of 3? f of 3 equals to 1. This is the minimum because we can just use 3 cents. And so on, right? Like f of 4 would equal to 2. We can use 1 cent and 3 cents. 1 cent and 3 cents. I'm sorry, in this f of 2 is not 1 and 3, it's 1 and 1. 1 and 1. Okay, now let's try to define the transition function. And this is where we can start sort of like brainstorming the problem, right? So what are our options here? So we need to find the minimum number of ways to make a change by using the following denominations, 1, 3, and 5. So let's say that we start making a change from 1 cent, right? f of I, and if we return 1 cent, we'll still have to return I minus 1. If we do the same with 3 cents, we'll have to return I minus 3 cents, right? If we do the same with 5 cents, we'll still have to return f of I minus 5. But the thing here is that we're looking for a minimum number of ways, right? The minimum number of coins, not the total, not the, like we are not using like we don't need to use sum operation here because we're simply looking for the minimum number of coins, right? So the minimum number of coins it's the minimum here, like this one is the minimum number of coins, this one is minimum number of coins, and that one as well, right? So we're not like aggregating all of these values, we're simply looking for the minimum, right? So when we are looking for a minimum or a maximum, it means it immediately like a hint that you should use the min. I need more space here, so I'm going to put this on. So it means that you need to use the min function, right? So we're going to wrap this whole thing into min. And now the other thing here is that every time we return a coin, right, we have to count this coin as a step, sort of like, right? So if I would have, because we are counting coins here, right? So if I return I minus 1, if I return, 1 cent, I have to count the cent that I already gave away, right? So I need to say 1 plus, and then the cent that I returned, I kind of like no longer count in the next state, right? So I minus 1. And the same is here, 1 plus f of I minus 3. Again, 1 plus f of I minus 5. And this is basically the transition function. So f of I equals to minimum 1 plus f of I minus 1, 1 plus f of I minus 3, 1 plus f of I minus 5. This is the transition function to this problem. It's super simple, and let's code it up real quick and see what happens. All right, let's see, guys. So given an unlimited supply of coins of given denominations, what is the minimum number of coins needed to make a change of size n? So the denominations that we are given are 1, 3, and 5. Let's start. So let's define an array of size n plus 1, we're going to specify base case dp of 0 equals to 0. So the minimum number of coins needed to make a change of size 0 is 0. The answer to the entire problem is going to be in dp of n. And now let's start our main loop. So starting from 0 all the way up to, we can start from 1 because we already know the solution for 0, all the way up to n I plus plus. And now we can, I'm going to set dp of I to math max int 64. This is needed in order to be able to identify if we were not able to make a change of size n. So maybe the denominations, maybe there is no way to make a change at all, right? So now we can say if I is greater than 1, then dp of I equals minimum between, I'm going to use my own min function, minimum between dp of I and 1 plus dp of I minus 1, right? If I is greater than 3, then dp of I equals min of dp of I 1 plus dp of I minus 1, 1 plus dp of I minus 3. And for the last case, if I is greater than 5, then we add 1 plus dp of I minus 5. And then lastly, if dp of I equals to math max int 64, then we can return something like, I'm sorry, not I, but n. Then we can return, let's say, -1. Let's run the tests and see if things work. Okay, everything is good. Now, as usual, let's drop all of that and try to convert it to a more general form. So for each coin, range coins, right? So for each actually j, we can apply the transition function. So dp of I equals total min dp of I 1 plus dp of I minus coins of j, right? And now we need to take care of the corner cases. So essentially, if I minus coins of j is less than 0, or if this value is less than 0, this is something you may not need depending on what kind of language you use. But in Go, if this value is max int for some reason, and then I add +1 to it, it will end up being negative max int. So I can also do something like that. Min int 64. So in this case, we want to continue. Let's uncomment all of these test cases and rerun the test. Awesome, everything is good, guys. Thank you so much. I hope this video was helpful. If you have any questions, feel free to post them in the comment section below. Thank you so much, guys. I'll see you soon. Take care. Bye.